All right, well, hello. Welcome to the first lecture of this course. I'm your instructor, Joshua Murillo. So let's get to it. Let's get into it. This first lecture is going to be a bit about, as the title says, math, some of the basic math concepts we're going to need kind of throughout this course in order to understand the physics more. Very minimal. The course is not meant to be mathematics-based or sort of non-mathematical overall. So just the minimal sort of things we're going to need. And then also a little bit about science, what it is, and yeah, also to give us a better understanding of the physics that we talk about later, as science is sort of the basis for how we go about doing physics and understanding the world around us. So let's do it. So as far as math goes, we're really only going to need the basic, or understand the basic operations, which I'm hoping you already do. I think most of us are probably going to be all right with understanding, the basics of addition, subtraction, multiplication, and division. We're also going to need an understanding of proportional relationships. When you say something's proportional to something else, or when it's inversely proportional to something else, what that means. I'll be going over these in the next few slides. And finally, some basic stuff about vectors. And vectors can be very, very complicated. You can do a whole lot of stuff with vectors. We just need some basic stuff. So again, this is just what's going to be going on here. So I'm going to kind of assume you got the multiplication, division, subtraction stuff. I'm going to move right into proportional relationships. When you say something is proportional, what you mean is that something kind of goes along in the same way that the other thing does. So if I say x is proportional to y, that means if I increase x, y will also increase. Or if I decrease x, y will also increase. It also means, since they're proportional, if I increase y, x also increases. The relationship goes both ways, just to say that if one increases, the other has to increase as well. Or if one decreases, the other has to decrease as well. So the opposite of proportional relationship is what we call an inversely proportional relationship. So essentially it's just the opposite of proportional. If A is inversely proportional to B, when A goes up, B goes down. Or when A gets greater, B becomes less. Right? So they do the opposite thing. Or when A goes down, B goes up. Right? So inversely proportional, essentially, it's just the opposite of proportional. One thing, whatever one thing is doing, the other thing's doing the opposite. Okay, so how about an example of a proportional relationship? One example might be that the number of pepperonis you're going to have on a pepperoni pizza is proportional to the size of the pepperoni pizza. So with a very small pizza, like the one on the left, you only get a few pepperonis on it. However, if you increase the size of that pizza, if you have a much larger pizza, assuming you have the same size pepperonis, you're just using the same pepperonis, you're going to end up with a lot more pepperoni on the larger pizza. And conversely, if you were even shrink it down even further, maybe you might end up with just one pepperoni on a pizza, or it might be just like a pizza bite or something. So the number of pepperoni on the pizza is proportional to the size of the pizza. Okay, so we could use a similar example for something that's inversely proportional. If you have a pizza and you're sharing it, the amount of pizza that each person gets is inversely proportional to the amount of people that are sharing it. So that means that if you just have two people sharing a pizza, well, you can cut the pizza in half. Each person gets half of that pizza. If you have 8 people sharing that pizza, and you're going to be nice and give everybody equal portions, then you cut that pizza into 8s, and everybody only gets an 1/8 of a piece, right? So the more people there are sharing this pizza, the less each person is getting. Right? So this is an inverse relationship. So we will use this kind of terminology or this notation sometimes, but don't be too worried if you don't get it so much. The idea is more important than the way it's written. But oftentimes in science and in many other things, many fields, people like to compact things, write them simply, acronyms, symbols, all kinds of stuff like that, right? So if I want to write that the number of pepperoni on a pizza is proportional to the size of the pizza, I can write it like this, right? I have a number of pepperoni on one side, size of pizza on the other side, and this funny little almost a looking symbol in the middle. So that funny looking symbol is actually a Greek letter. It's the letter alpha, and it's used in proportional relationships to show proportionality. Right? So if I see this, I would read it off as number of pepperoni is proportional to size of pizza. Or another way to read that off is sometimes you might say the number of pepperoni goes as the size of the pizza. So if the size of pizza goes up, the number of pepperoni goes up. If you want to represent an inversely proportional relationship, well, you use almost exactly the same thing, except for one of those sides is in a fraction where it's 1 divided by that other thing. So in this case, number of people sharing a pizza on one side, and then 1 divided by the amount of people, or the amount each person will get, the amount of pizza each person will get. So this is showing that if the number of people goes up, the amount each person will get is going to go down. Or if the amount of people they are sharing, or the amount each person will get goes up, then the number of people sharing it has to have gone down. So they're inversely proportional. And you would read this off just like, similar to the first one, number of people sharing the pizza is inversely proportional to the amount each person will get. Or the other way of reading it is the number of people sharing goes as 1 over, or 1 divided by, the amount each person will get. So some examples of proportional and inversely proportional relationships. In physics, we're going to see some of these in the next lecture, I believe, but just as a kind of a preview, the speed of an object, the speed that an object is traveling, is proportional to the distance it travels in a certain amount of time. So if you have an object that's traveling from point A to point B, say like Napa to San Francisco, well, if it travels that distance, and then it travels a greater distance in the same amount of time, so the distance it traveled increases, the speed of it had to increase too. An inversely proportional relationship is actually speed, the speed of an object is inversely proportional to the time that it takes to travel whatever distance it's traveling. So we're going to take a distance, say from A to B, and if it takes a certain amount of time to travel there, and then the next time you do that same journey, whatever it is, and you take half the time, right, decrease the amount of time it takes to travel that distance, the speed has to increase. Right? So those are inversely proportional to each other. One goes up, the other goes down. Or one goes down, the other goes up. Same thing. Some other examples, which we'll see a few lectures from now, or come back to at least, is the acceleration of an object. So how this speed and the direction of an object is moving, how that changes over time. Right? So in simple version, speeding something up or slowing something down, accelerating, decelerating. That actually depends on the total force that's being applied to that object. Don't worry too much about what that means right now, because we're going to talk about it later on, or more later on. But it's also true that the acceleration of an object is inversely proportional to the mass of that object. The other math concept we're going to need, at least for a good bit of the course, is the idea of a vector. And a very simple idea or concept or way to think about a vector is just an arrow. So an arrow, if I was holding an arrow, I don't have an arrow, but if I was holding one, it has a certain length to it, and it is pointing in a certain direction. So if I had an arrow and I'm holding it straight up, it's this long, and it's pointing straight upward. Right? Or if I turn it to the side, it's still the same length, but now it's pointing that direction. Right? If I chop it in half, it's half the length, but it's still pointing that same direction that I was before. So an arrow has these two qualities that determine, or kind of, define what that arrow, or define the arrow, I guess, overall. And the same thing goes for a vector. So a vector, just like an arrow, has length, often will be referred to as magnitude, like the size of that arrow, and it has a particular direction, right? It has to point in a particular direction. Sometimes some examples might be if you have an actual arrow, it's 2 feet long and it points, say, to the left. Or you have an arrow that's 1 foot in length and it points up. We'll learn more about stuff like force and velocity later on, but it turns out that force is a vector quantity is what you'd say. And an example might be you have an arrow that's representing a force, and it's saying 10 newtons of force applied to the right. So don't worry about what that means so much. It's just the fact that a vector is something that has a magnitude, it has an amount to it, and it points in a direction. So similarly, you might have a plane that's flying, and you could represent its velocity, the speed and direction it's flying, with a vector. So that vector is representing a speed of 500 miles per hour, maybe, along with the heading southeast. Right? So both of those things are needed in order to define the vector. And every time you're talking about a vector, if you're going to be fully describing it, you need to say what is its magnitude, or what is its length, it's the amount of it, and you need to say what direction it's pointing. Okay, so that's it for math basics, and now we're going to talk a bit about science. So you've probably gotten some kind of overview or talked to about science at some point, and to be honest, this might not be that much different, but I think it's useful anyway, so we're going to talk about science. Like, what is science? Well, it can be fairly well summed up as just saying it's a body of knowledge. You can imagine it as like a library somewhere that's just filled with books of all the different things that humanity has found out. It's an ongoing activity. It didn't just start and stop at some point, right? It's still going right now. And it's something that actually preceded recorded history. So the drive to do science and to explore things scientifically, maybe it wasn't codified or put into such sort of stricter language and ideas until much more recently, in the last, a few hundred years, several hundred years. But, way back when we still lived in caves or something, they were doing something to figure out that you could make fire if you struck the right rocks together and had some tinder lying around, right? So in that same sort of effort of trying things and seeing what works and being curious overall is sort of that scientific endeavor. However, science is necessarily based on measurement, experimenting and measuring or observing things. Well, I'd say the reason that is mainly because science is worried about how the world actually is. So it doesn't matter if you make up something, it's the most beautiful theory that there ever could have been. If it doesn't agree with what nature does, it's wrong. Who cares then, right? So you need to be able to measure things, you need to be able to go out in the world and observe things and see that they can verify your theory or they might disprove your theory. And this is a nice quote from one of the founders of quantum physics, Max Planck, and he said, an experiment is a question which science poses to nature, and a measurement is the recording of nature's answer. Part of the reason why I started out this lecture with mathematics and some math basics is because even though this is a non-mathematical course, math is fundamental to science, right? Math is essentially the language of science. If you want to communicate things unequivocally, then we use numbers, we use equations, matrices, graphs, all the kinds of things like that. You could say that science became much more rigid, or not necessarily rigid, but much more along the lines of how we understand it today once mathematics was starting to be included in the scientific endeavor. And once people started deriving or coming up with equations to describe things happening in the world, and then using those equations to predict new things, and then going back out in the world to see if those new things are actually there. So, not super important that you remember all of this. This is not the most important part of this course, for sure, but I think it's a good thing to just be introduced to, and maybe keep in mind as we go through the other lectures that as much as I'm going to try to explain the concepts of physics to you, I can only really go so far, and, well, some of you might actually be intrigued enough to go further, and you'll find out that you really do need mathematics, and there are concepts that, I've encountered concepts myself that, it was really difficult to make sense of. It didn't really seem to mean anything concretely, but mathematically it made sense. And eventually it just becomes more apparent that that is sort of the truth at some level, and you just kind of have to sort of accept it, and it becomes part of your reality, I guess. Okay, so scientific methods, right? And first thing to say is there really isn't one scientific method. If you have seen a presentation or somebody tell you about the scientific method, what they're explaining is the kind of the most common idea of what the scientific method is. But the way you actually go about doing science and scientific exploration, it can vary wildly. So the actual process of doing it can vary a lot, but in general, you sort of rely on some principles, which is, well, being systematic, not just leaving things out because you can, right? You gotta explore all the possibilities. And like it goes into a lot of different ways, but essentially you're trying to answer some kind of problem. You're trying to figure out why something is, or the way, how something is the way it is. And then beyond that, you actually are collecting data, you're making observations, you're going to look in the world to actually see what happens, what's out there, and formulate an idea, a hypothesis about why it is like that. And then when you go out into the world, you can test your hypothesis to see if it's true or not. Okay? So you take your whatever idea you might have come up with, and you try to make predictions as to something, how something will work that you haven't yet seen. And then if you can go out into the world and you can find that thing and it does what you think it's going to do based on your hypothesis, then you say that hypothesis was probably true, or it was correct in that sense at least. Alright, so let's just look at some common steps for the scientific method. So first you would recognize a problem, a question, some kind of unexplained fact, right? See something is puzzling, you don't know what it is or why it is the way it is. Then you make a guess as to why it is that way. You make a hypothesis. And your hypothesis explains why the thing is the way it is, or how that puzzle sort of fits together. With that hypothesis, you try to sort of extend the hypothesis to other areas. You say, well, if this explains the puzzle I thought about, what would it say about something else that's close to it, or something else that maybe is all the way in a whole other field, or something like that. But any hypothesis is going to have consequences in other areas beyond the thing you just were thinking about. So you sort of make predictions with that hypothesis for other things. Then you can go out and you perform experiments, or then you make calculations to test those predictions. So if you said, based on my hypothesis, X, Y, Z would happen, you go out, you do an experiment, and X, Y, Z happens, then that's a pretty good hypothesis. You'd say that was you verified your hypothesis there. Though it's not necessarily still 100% true, it might fail in other areas, right? But it's a way of testing out your hypothesis. And finally, you would sort of formulate the simplest kind of general rule that organizes your hypothesis and how it resolves the puzzle. In a sense, you're essentially just kind of formalizing your hypothesis and putting it into a format that extends beyond just the puzzle you initially were thinking about. And there you go. You have a scientific theory. Okay. What is the scientific attitude? What is the attitude of a scientist? Well, as we all know, everybody's attitude varies. One day, 1 minute to the next, maybe. In an ideal world, a scientist would be a person who has this attitude of inquiry. They're inquisitive, they wonder about things, they want to know why things are the way they are. Experimentation, they are not satisfied with just guessing why the thing is the way it is, or thinking that they're right. They have to go and test if they're right or not. And very importantly, a willingness to admit error. If you think you're right about something and you make a test of that guess, and the data comes back or your observation contradicts what you originally thought, you need to be willing to admit that and to change your thinking, to think about it in a different way, or to accept that it's different. Beyond that, scientists, you need to accept, very related to the last one, you should accept valid experimental findings. So if somebody does experiment, they report results that are unfavorable to you for some reason, you gotta accept it. That's how science works. Science doesn't care if you like it or not. You should be testing for erroneous beliefs, meaning that we all have beliefs that we don't really think about that much, and sometimes they're very fundamental to our lives, actually. But as a scientist, and particularly when you're thinking about a scientific endeavor or something, a field or a topic in science, you need to explore all the ideas or the beliefs that go into that and make sure that there aren't fallacious ones in there, there aren't illogical things going on in there. And also understand objections and positions of antagonists. So people who disagree with you, or who have a different idea of why something is the way it is, you shouldn't be dismissive of that. just because you don't like it. Right? The whole point is that you should actually, if you're going to be a proper scientist, you need to understand their theory just as well, or hopefully as well as they do, in order to understand why they might think you're wrong. And in that case, maybe they do convince you, or maybe you now understand their stuff enough to better explain yourself, and so you convince them that you're correct. So this is it's a back and forth sort of thing that will happen in science. So, there's this underlying thing that you might have picked up on in the last few slides, is that science is really driven by this question of why a thing is the way it is, or how something happens, why it happens. But at a very basic level, why? Just why? The way I think about it, at least, is that that driving force to ask that kind of question is our curiosity, just as humans, right? We're naturally a curious creatures, and that drive to understand why or wonder why something is the way it is what drives science. We're going to talk about a lot of different concepts in physics in this course, right? We're going to run pretty much the entire length of physics. We're not going to touch on everything, but we're going to talk about just about every sort of field, generally speaking, in physics, right? And all of those fields, all of that we understand now, could be traced back in some way to somebody at some point wondering, just like, I wonder why that is, right? And then exploring that. Okay, so back to hypothesizing, or a scientific hypothesis. One of the most important things about a hypothesis, right? This is your educated guess as to why something is the way it is. One of the most important things, and a crucial thing, necessary thing for it to be scientific, is that it must be testable. Meaning that there needs to be a way to prove it wrong. Even though that test might fail and it's still shown to be correct, there has to be at least a way to test it. So some examples of possible scientific hypotheses, right? One, you could say, well, the moon is made of cheese. That's my hypothesis, right? I've seen the moon, it looks like cheese, I'm gonna guess it's cheese. That is actually a scientific hypothesis. As silly as it is, it's scientific because you're making a hypothesis, and that hypothesis is testable, right? This is my statement, the moon is made of cheese, okay, go and test it, right? Shoot a person, shoot a robot, shoot something up to the moon, grab a chunk of it, bring it back, test it, nope, that's wrong. Yep, that's not cheese. All right, we tested it. There we go. And it was possible to test it and prove it untrue. Could have turned out the moon was made of cheese. Who knows? Well, we know now. But before we knew, it's a possibility, right? And it's testable. That's the key. The second example here, a unicorn's urine is rainbow colored. It comes out like a rainbow. This is not a scientific hypothesis. Why? Because there is no way I can test it, right? If there were unicorns, then I could test that hypothesis, right? Wait out some in their natural habitat and wait until you see one doing its business and identify if its urine is rainbow colored, right? There you go. That's how I would test it. The problem is I can't test it. Right, so not scientific. It's a hypothesis, it's not a scientific hypothesis. Right? And this quote sort of encapsulates that idea that a hypothesis needs to be tested, or needs to be testable, and be able to be potentially proven wrong. Okay? So this is actually from another founders of quantum physics, Wolfgang Pauli, and he said, this is after somebody had told him about a new idea in science or in quantum physics at the time, and his response was, that's not right, that's not even wrong. Right? Essentially, I can't even prove that's wrong, why would I even care? It's not a scientific hypothesis. Alright, and finally, talking all about science, right? So physics is one of the main branches of science. Technically, there's different ways to think about the categorization or the branching sort of science. Physics is part of what we would call the physical sciences, and those are, say, geology, astronomy, chemistry, physics. And then you also have the life sciences, things like biology, zoology, botany. But physics is sometimes called the basic science, sometimes called the fundamental science, because it underlies all the other sciences. The concepts of physics are in use in all other sciences. Things like mechanics, like how things move, so the stuff we're going to start getting into next time. Things like energy transport or heat transfer. Things like wave motion or oscillations. These things are all described in physics and utilized in the other sciences. So this is just a definition of physics, pretty broad but not that bad. And something that I'll probably point out multiple times throughout this course, just to remind you that when I tell you about something, I do my absolute best to tell you the truth, or tell you as much as I can within the limits that this course offers. Right? Generally, if you're taking a mathematics-based course in physics, it's going to be 2 to 3 semesters for them to cover pretty much the same sort of set of material that we're going to cover in this one semester. Right? So we're limited by time, and we're also limited by the language I can use. Right? So I'm not going to rely on mathematics very much, but that also is good for you maybe, but it's limiting also to understanding in more detail. Right? So for the most part, we're really just looking at like the very simplest version of whatever topic we're going to be talking about. We're kind of scraping the surface, and there's all kinds of stuff underneath. All right, well, that's it for the first lecture. It's going to be a little bit on the shorter side, so it's fine, good for you. And that's all I got, so see you next time, and have a good day, or evening, or morning, whatever it might be.